Hello, community. Let's have a look at the latest research by MIT on neural scaling. We have a new publication out today, and they explain now neural scaling. And the answer to the question is bigger always better, especially for AI systems. Let's start. We have multiple AI agents that we code. We have our MCP protocol. We have agent-to-agent communication, which is great. And we have, in general, our agent memory. We have LoRa adapters for the training. And the intelligent core of an agent is our LLM. And normally, if we train now this LLM on multi-agent tasks for each agents, we have an LLM and we have different adapters for each and every agent. So we train here only, if you want the fine-tuning or reinforcement or learning, with our adapter structures. But you know what? We still have the main intelligence in the LLM, in the core. So how small can we go with our LLMs before the performance simply breaks down? And this is now where the power laws for neural scaling come in. Because if you say, hey, I don't mind, I pay whatever it takes for the best OpenAI model, great, you have no problem. You go with the most expensive and with the biggest model that is available. But if you want to work locally or you don't want to spend the money, the power law provides us now new information. Have just a look here at the benchmark data for the QN3, 22 billion free trainable mixture of expert model. Performance is 81. How is it possible that it outperforms the Grok 3 beta? The Grok 3 beta should be much bigger than the 22B, no? Well, this is the question we're going to look at. Or look at this, at AIM24, the benchmark here, a little 4 billion free trainable parameter outperforms with 73 a GPT-4 Omni that has just a performance index of 11. How is it possible? Bigger, and I suppose GPT-4 Omni is much bigger than a 4 billion dense LLM. How is it possible that this is so much better? Yes, it is newer, but what about the neural scaling laws? What's happening here? Now, in general, we can say that bigger language models always perform better. And there's even a predictable pattern, if you want, a power law that helps us to understand exactly how to scale LLMs. If you're not familiar with power laws, no problem. We have linear relationships like this one. We have exponential relationship like this formula. And then we have power laws that are given here. They have two very beautiful behaviors I'm going to talk about in 10 seconds, the scale free and the heavy tails. And we have power laws in neural scaling. Let's explain why and what they do. Now, the mathematical notation for this is simple, this one, where we have your y and your x are the variables of the system. You might have here a constant scaling factor called k, and n is now interesting here, the exponent, a real number, positive or negative. Now, we do have a scale invariance of the power law relationships, and even more important, we have heavy tails. Now, we come back to this in a minute. So the scaling of the loss is now something that we say, now in the AI system, we talk now about the parameters x and y, and the first parameter is here the loss of the system if we do our training. This is here the optimization, the objective function. So the scaling of the loss, and the second parameter is the model size. And we know that the scaling of the loss with the model size is here crucial, plays here a central role in the design of new LLMs in our theoretical understanding of what is happening here in machine learning system. We do have here a particular neural scaling law where we say the loss decreases as a power law with the model size or the dataset size or the compute, and this here is a simple relationship. Years ago, we were talking about the chinchilla scaling law, and you remember there was this particular parameter, and today MIT gives us here an explanation why this is happening. So here we have a brand new study, May 15, 2025, Massachusetts Institute of Technology, and the title is Superposition Yields Robust Neural Scaling. And you might look at these diagrams here, and if you are really deep into the topic, you immediately understand what is happening. But if not, let's start from the beginning. It is not easy, but we will do it. So, why do bigger models almost always outperform here the smaller models? Now, MIT tells us, well, it has to do with something we call a superposition. What is it? It is not a quantum superposition. This is a classical one. But let's do two different explanations. A simple one and then a little bit more complicated, and then we go for the real stuff. So just imagine, to give you a feeling, a language model, and this language model has a certain workspace, a mental workspace. You know, it's the hidden dimension here of an AI, but never mind. And it needs to represent thousands or even millions of different words, of different concepts, or different features. Now, if the workspace is real small, and in particular if it's smaller than the number of things to represent, the model can give each feature its own private, clean spot in this space. Instead, it has to cram different objects together that it will fit in this given state. So superposition is now, if you want, an act of cramming. Multiple features are represented using your overlapping patterns within the same limited neural dimensions. It is a little bit like pure chaos. Now, think about this now in another example. You have 4 projectors and you have 4 information. Let's say the information you want to encode are simple words: apple, banana, happy, and sad. And the projector can shine now different wavelengths. Let's say red is encoded here for apple, blue for banana, green for happy, and yellow for sad. Plus, red is in a particular subspace of its own. Top left corner. Blue is at the top right corner, green at the bottom left corner, and yellow at the bottom right corner. So you see, we have defined subspaces for particular encodings. Great. Now, if we have no superposition, it's really easy, no? If you want to encode the signal apple, you only have projector 1 shines a red light to the top left corner. All the other spots are dark. I have an absolute clear signal. I know exactly that the message is apple. This is that we have an orthogonal base and eigenbasis. If you have, for example, a hidden space in 3 dimensions and you encode here 3 different features, you have no superposition. This is great. But imagine you have now 10 different messages with a lot of different further information that you want to encode here in the same space with the same 4 projectors. Now what you do is, the signal for apple cannot be now a single projector, but is now a combination. So you turn on for apple a strong red light and a faint blue light. So 2 different projectors now with different intensity. So you see how you encode this further. But for example, Jerry now has also a red light and a medium yellow light. So here Jerry, if you want, shares the red one with the apple. So you see we have overlapping vector representations, or here color representation. And of course, we are here in a mathematical space where we have a non-orthogonal base. Now, the consequences of our non-orthogonal vectors is, on the one hand, great, because we can represent now more than 4 messages with our 4 projectors. But we have to cram them together. We have not clear signals anymore. And maybe some signal is not really clear in the interpretation. Maybe one color is too faint to be noticed by the sensor or whatever. We have noise in the signal. And you know from signal theory, whenever we have noise, this is more or less an analogon to our loss that we have in the neural network when we train our neural network in the objective function. So this means if we put now more information, so more feature vectors, into training data, into a smaller space, into a smaller hidden dimension of our neural network, those vectors, input vectors, cannot all be orthogonal, cannot all be clear signals. So they have to share some parts of this dimensional space. like I showed you with the colorful projector. And this sharing is exactly what we mean with a superposition, and this leads to interference. But it also, and this is the positive part, allows the model to represent a rich world with limited resources. Now, MIT tells us there's something strange happening, because if we go for a weak superposition, we have a different scaling law, and if we go for a strong superposition, the power law changes significantly, and we have a new non-dependence that we discover in the system. So, let's explore this. Yeah, of course, there's a relation to my other video where I showed you here about in-context learning. How does in-context learning work inside the transformer, inside the different layers of a transformer with the activation space? Here we are talking about the representation space. And yeah, you know, of course they are related. So let's look now a little bit closer here to this MIT study, Massachusetts Institute of Technology, May 15, 2025. And they tell us here, when more and more vectors are packed into a lower dimensional space, the interference between the vectors scales inversely with that dimension. And you might say, this is interesting. And when we analyze 4 families of open-sourced LLMs, our real-life LLMs, and found that they exhibit here a strong superposition and quantitatively match the prediction of our toy models, they could now explain, for example, the chinchilla scaling law. So let's have a look what they did and how we can understand this. At first they started here with a model, but with a simplified model, a toy model, what they called. Here you see the toy model here at the top of your screen. So what we have an input space, we have a data space, and here our input information. Now what we want to do, we want to encode this information in a lower dimensional mathematical space. We want to compress this information, and then we want to decode this information back into a new data space where we can define the loss and a loss function. And this loss function is the objective function. And then the model tries simply to minimize this loss. And what we achieved is we have now from an original data space, we found now a more condensed hidden space with a model dimension of m that is smaller than the data dimension n. How we do it? With a weight matrix. You know this. So the encoding process is simple as you see in this formula. And of course, in our tensor weight matrix, the quality of this space H depends how well W has been learned for this complete process. And if we have then a hidden space representation here in a lower dimensional space, and we decode it back with the weight matrix now, you see the generated data space should be as close as possible if we calculate the norm, the difference here with the loss function, and then we just have a function that we have to maximize or minimize. Now, if you look closely, you see that here the data space Y has, of course, it has here the nonlinear ReLU function that we need. But if you think here about this, we ignore the bias, the B for the moment. You can see we can solve this into, if you want, kind of an inner product, a W times W transpose. Now it becomes interesting because if we look at this particular term, this is the dot product here, if you want, in no superposition configuration. So let's say we have 6 features. In no superposition, the system might decide, hey, I just encode from these 6 features. I have 3 dominant features and 3 very weak features, and I only encode the dominant features. You see exactly, if we calculate now here the diagonal, that we have non-diagonal elements or 0. And you see we only have here the first 3 dominant features, and the other 3 features that should be there are not there because if we look here a frequency to rank, they have a lower frequency, they are weaker, they are not as dominant in the training data, and therefore we can decide, hey, we just go here with the high frequent data, the first 1, 2, 3. And we ignore the rest. Now, question for you. What is the noise in this system? Well, the noise in this system here that will generate here or have an impact on the loss function is, of course, the missing features. Now, the thing is completely different if we go now and we say, hey, let's do this superposition. So we say, beautiful, we encode now all 6 features here in this 3-dimensional hidden space. Let's go with this example. What we have is suddenly in our diagonal matrix, we have all elements equal 1, but just look at the off-diagonal elements. Everything is here, everything is active. We have a complete mixture. So now we say here, we do not only have the top 3, the most frequent features that negate now a strong representation, but now we find a representation that is mixed, the off-diagonal elements here, and we can encode all features. So this is the way our LLM work. Absolutely fascinating. Yeah, so this means that the representation learning is more or less tied to the embedding matrix and the language model head, like we talked about here, also in context learning. And now they did some experiment, and this is now interesting because now we decide between the weak superposition scenario and the strong superposition scenario. So weak, we have a hidden space of our toy model of 3, and we have just 3 representation vectors, so beautiful, no superposition, everything is clearly separated orthogonal basis. And if we look now at the feature for a linear decay, a power law decay, and exponential decay, you see they have this particular curve. If we go to the strong superposition, you see suddenly a new dependence, a new behavior. And they did this not just here in color for the toy models, but they also used actual LLMs for this. And guess what? They found that the actual LLMs are all here within the strong superposition scheme, which makes sense, no? Given what model you take, and you only have, I don't know, whatever you go with the hidden dimension, 5,000 or 50,000, and you have to encode the complete internet, you do have to have superposition. You have to have strong superposition. So, let's have a look at the benefits and the problems if we only have a weak superposition. So the model learns primarily distinct, clean signal, clean representation of the most important or most frequent features in our training data. So the main source of error, this is in our case for AI models, the loss, comes from the features that the model did not learn well or ignored completely. So now we understand that the loss function is dependent here on those missing subspaces, the information that we don't take in. But there's even a more interesting fact. This is about the long tail. Because how quickly the model improves now if we increase the size, this depends heavily on the long tail of those ignored features. So our data features, whatever they are, either they are words or either they are specific reasoning patterns, if you look at the frequency spectrum of those, and you can see a long tail developing, then this will tell us something about the performance of the AI system. Why? If the ignored features quickly become very rare in our feature spectrum and unimportant, then even a small increase in the model size can lead to a big drop in the loss function, because now suddenly, even if we increase the model size just for a tiny step, we have these features that are now rapidly declining within our calculations. If those features here in the tail are not as diminishing as rapidly as we think, but just doing a little bit, well, the improvement is less dramatic. So the key is if the scaling law, and this means how the loss decreases here with the model size, becomes real brittle, it is very sensitive to the exact statistical properties of the data, the feature frequencies, and how those feature frequencies are distributed. And if the feature frequency follow a power law, the loss might too, and if not, the loss scaling might not be a clean power law. So now we understand that given a particular task, the behavior of the system is different because the data distribution itself is either a clear power law or something else, and this has a direct feedback on the performance of the AI. MIT, absolutely beautiful to have this new understanding. Now, strong superposition, I called it the cramming, you cram everything in, is of course the other way. If a model tries to represent all of the features in the input training dataset, even the rare features, and we have only a limited workspace, the hidden dimension of the system, then we have to force intense overlap between the feature representation. So every feature gets some representation, but no representation is really clean. We have no clean signal. It is always mixed together with other signals. And this means the main source of the loss now comes from this interference between those overlapping representation. Because the system has now tried to learn here a perfect representation in this reduced representation space, where it can clearly distinguish between the overlapping representation, and this is not easy. So when the model tries to use one feature, hint of other features or a similar looking feature in the representation space get also activated, and this is causing absolute confusion. And maybe if you think about hallucination, we have here one other parameter that might theoretically contribute to this. This is now the moment where a new fundamental geometric principle kicks in. Let's say you have n distinct vectors in a much smaller number of dimensions, and now we have the geometry dictates now if n is much larger than m, these vectors must overlap significantly. And this average square overlap, this is a measure now of the interference, will be roughly proportional to 1 over m. This is a geometric feature. So this means as you increase the model's workspace size m, the average interference naturally goes down as 1 over m. Now what is absolutely fascinating, this scaling now is robust. It tends to decrease proportional to 1 over the model width, regardless of the fine-grained details how the feature frequencies are distributed. Isn't this fascinating? So you don't have to care about the feature frequency distribution of your specific features if you do a reasoning task, for example, or have a representation for medical or financial data. You can just say, if I have this condition of a strong superposition, I can know that the scaling law is robust and that the loss tends to decrease proportional to 1 over the model width, independent of the frequency distribution. This is now absolutely interesting. And if you look at our real LLMs, we see they operate here in the strong superposition regime. Of course, it was expected, and their empirical loss scaling now matches here the 1 over m model width pattern predicted by the strong superposition theory. MIT, beautiful insight why this is happening and to present here the solution. So this robust power scaling law of LLM loss with the model size is now not just an arbitrary empirical observation till it was until now, but now we can theoretically understand, and there's a lot of mathematical models in this paper by MIT that I'm not going to show you right now here, because I'm just focusing on the main idea, on the main insight. And if you go and have a look at the experiments, please read the paper. Theoretically understood as an emergent consequence of the model learning representation under the strong superposition. So this means we have geometric constraint of compressively representing many features in a lower dimensional space, and this is the reason why this happens. So this means now we have a more fundamental understanding of why current LLM architecture scales so well. But this also means that we have, if we do design further the next generation of AI, we can guide here the future research in making models that are even more efficient by understanding now how a good superposition is important for the performance of the system. I have here some thoughts of my own. Let's have a look at this. Because what is the impact for you? Now, You know that we have this huge closed OpenAI and Google LLMs. And you know what? This ChatGPT, for example, must be a model for all 8 billion people on our planet, or how many billions it is right now. But if you say, I want to now have a special AI, if you have only a clearly defined AI task, let's say you only work in finance, or you only work in medical, you only work in chemical, you don't need those huge models where you have representation of, I don't know, English from the 16th century or some French poems from the 14th century. You don't need all of this. If you have a dedicated expert AI system, you know what? This scaling law tells us now something, how small we can build our agents, because we understand now how small we can build our intelligent core, our LLM. So if you design now your special LLM, this local LLM can be much smaller, but smarter, because now we can do a representation space optimization for my features. My features here, for example, is theoretical physics, is the law of thermodynamics, the law of mechanics, the law of special relativity, of general relativity, of quantum field theory, you know, absolutely reduced representation space. My features are purely theoretical, mathematical, physical features that I want to represent in my LLM. Maybe you only want to have financial features, financial forecast, financial trend analysis, or financial whatever you want, foresight. Then you don't need those huge Google LLMs where you have to pay for the cloud. You can build this locally. So this means that you have to pre-train those systems on your specific task and the features that you build your local LLM for. So this now means that we can have beautifully small edge agents that are much smarter, have a better performance than an agent that has here access to a cloud OpenAI model, because we have now expert agent that are really dedicated from the pre-training to their specific task and their features. So, absolute fascinating new paper by MIT, how to build small and smart cores of our AI agents, local LLMs, with a representation space optimization for the particular features that you build this expert agent for, and only those features. And you can make it small, much more powerful than a cloud-based OpenAI LLM. You can build it here locally on edge, and it has an outstanding performance. If you're interested to learn more about this in the next videos, hey, why not subscribe, and I see you in my next one.